Let's go ahead and get started. Um, so the topic today, what I want to go over, um, hopefully I'll get you out of here before 7:20. I don't think it'll take the whole time today to get through all the material from these lectures. But one of the topics that you'll be actually doing two different labs on this semester involves calorimetry. And so I'm just going to take you through an example of how to analyze the thermograms that you're going to get when you do calorimetry. Okay, because in the past there's been a lot of confusion and questions about this. So I just wanted to include this in the lecture. So, okay, what do I mean by a thermogram and what do I mean by calorimetry? Well, calorimetry is basically a method to measure the heat of a reaction, right? So the enthalpy of a reaction by measuring changes in temperature. And so in this example, one of the labs that you're going to do involves using a special type of calorimeter, which is called a bomb calorimeter. It's not going to explode, don't worry. But it's a type of calorimeter that's used to look at reactions that happen in the gas phase. And you're going to look at, I think you're going to measure the heat of reaction or the heat of formation of naphthalene. And so basically the way you do that, you set up a sample of naphthalene inside of this vessel here. The vessel's filled with oxygen. There's a wire coming out of the vessel that's attached to an ignition, which you ignite the wire. It initiates the reaction. The naphthalene is going to combust. A certain amount of heat is going to be released, and then you're going to measure the temperature change of a water bath that's in thermal equilibrium with the calorimeter. And if you know the exact heat capacity of the calorimeter itself, then you can use the temperature rise that you measure to calculate how much heat was released by the chemical reaction. And then you can do some calculations and figure out the heat of formation of naphthalene. Okay, so that's the basic idea. Yeah, you're also going to use this in a solution phase calorimeter, and you're also going to get thermograms in the experiment that you get when you measure the freezing point of depression. So this topic is going to apply to actually 3 different lab reports that you're going to be responsible for this semester. Okay, so what does the data look like that you're going to get? Well, here's a typical data set that you might see for the calibration experiment, which is the combustion of benzoic acid. And so basically, in this experiment, you measure the temperature of this water bath, right? Before ignition, it's equal to some steady value. Here's where you ignite the sample. Then you start to see the temperature rise. Eventually, you'll see it level off. And then, over here, this is the final temperature. Okay, but in order to get the most accurate measurement of the heat of reaction, the manufacturer of the bomb calorimeter has a recommended method that you use to analyze these thermograms. So basically, you're supposed to take the pre-ignition period and extrapolate forward what the temperature is, and the post-ignition period where the temperature levels off up here, you're supposed to extrapolate a line based on this data in this direction, and then the difference between these two extrapolated temperatures at the point where the thermogram goes through has reached 63% of its total rise, right? That's the temperature at which you're supposed to measure the difference between the initial temperature extrapolated and the final extrapolated temperature. Okay, so just to show you that a little bit more explicitly, let me see if I can find the figure from the lab manual. Here we go. So the reason why you do it that way is because sometimes you don't get a nice flat baseline like in the data that I showed you. Sometimes there's a drift in the temperature, right? And so in this example here, the temperature before ignition is drifting upward slowly, right? But this has nothing to do with the chemical reaction. This is just, it's getting hot outside or something, and the lab temperature is rising a little bit. And so at this point, the reaction gets ignited, there's a temperature rise, and then after it reaches its final temperature, it's actually still drifting upward a little bit. And so by fitting this line and extrapolating it backward, you get the temperature rise should be the difference between these two extrapolated lines, somewhere in the middle. And the point where they recommend to measure this is exactly 0.63, when this curve reaches 0.63% of its final value, right? So the distance from here to here should be 0.63 of the total distance between here and here, right? That's the time at which you want to measure the difference between these two curves. Okay. Okay, so how do you do that? Well, I'm going to step you through an example. Okay, so here is a spreadsheet. I've gone ahead and plotted some data. Let me make this just a little bit bigger for you. Okay, so here's an example of some data. So you recorded the temperature at intervals of one reading every minute. And here's what the thermogram looks like. It's the same one that I just showed you. Okay, so we're going to analyze this thermogram. Okay, and so the way to do that is first extrapolate a line based on the data before the ignition, and then extrapolate a line based on the data after the ignition. And sometimes students are confused. How do I do that, right? I have this data set here. If I go to add trend line, then I get, this weird looking line that goes through all the data, right? That's not what you want. You want to pick only the first few data points and fit a line to that data. So how do you do that? Well, the easiest way to do this in Excel is to add another data series to the same graph where you choose just that data that you want to fit to a line. So I'm going to right click on this graph. I'm going to click select data, and I'm going to click this plus button to add another data series to this chart. Then I'm going to select the X values that just correspond to this initial set of data before the ignition. So maybe the first 5 data points. So I'm going to choose the first 5, 1, 2, 3, 4, 5 X points, and the first 5 Y data points, 1, 2, 3, 4, 5. Okay, and then I'm going to get, if I click OK, I get another data series that's now shown in orange, and I can fit this one now to a linear extrapolation. Okay, and then I can also select the data at the end. So I'll add yet another data series. The X values, I'll just choose maybe, I don't know, 1, 2, 3, 4. I could choose a 5th point. Maybe, if you really look closely, it looks like the data starts to curve down at around the 5th data point. So maybe I'll just choose the last 4. There's a little bit of a, qualitative judgment that goes into choosing what part of the graph to extrapolate. But I'll just take the last 4 data points. Okay, and now I have 3 data series that are all going to be shown on this graph. Unfortunately, the color of this last one looks almost like the color of the middle one, so maybe I'll change the color. So if I go to the marker fill options, maybe I'll change it to purple or something, so it'll just show up a little bit clearer. And I'll change the line to the same color as well. Okay, so now you can see there's a blue curve, but then I've taken part of that curve and I've shown it as an orange data set and a purple data set. Okay, and so now I want to take this orange data set, so I'll click on the orange data points, and we want to extrapolate a line, so I'm going to add a trend line. So I'll right click and go to add trend line, and then this trend line menu will open up. Just like last time, you can display the equation on the chart and the R squared value if you like. There's another option, however, that we didn't talk about last time, which is there's an option to forecast the linear trend line forward or backward. And so in this case, we want to extrapolate this linear fit forward. And we want to go forward, maybe a few hundred seconds. So I'll say I want a forward forecast of 300 periods, maybe something like that, or maybe 400. So it goes all the way to the end, something like that. Okay, and then if I click on this other data set that's just these 4 data points at the end, I can do another linear extrapolation, add a trend line, but this time I want to extrapolate backward. So I'm going to forecast backward by maybe 400 seconds or so. Okay, maybe 500. Okay, and now I've got two extrapolations, and so we want to find basically the difference in temperature between the start and the end by reading the temperature somewhere here in the middle, right? So we want to know the difference between this dotted line temperature curve at the end of the experiment and this extrapolated dotted line, somewhere here. Okay, so what we're supposed to do is figure out the time, right, at which the data or the rise in temperature is equal to exactly 0.63 of the total rise. Okay, so how do we do that? Well, if you read the procedure in the lab manual, they recommend that you print out your graph and take a ruler and try to estimate where's the point at which the rise in temperature is 0.63 of the total distance between these two extrapolated curves. You can do that. That method works great. If you don't have a printer and you're just working on your computer, you can also just do it on your computer. And so one way to do that would be first just make an initial guess of, at what point in time is this curve approximately reach 0.63% of its, final rise value. And so maybe that's, I don't know, somewhere here, 400 seconds, maybe a little bit earlier, but 400 seconds, that's good enough, just an initial guess. So we want to know what is delta T at little t time equals 400 seconds. Okay, and so we're also going to want eventually to get some statistics so that we know the error. So I'm going to go ahead and calculate two different line est functions. So I'm going to calculate a line est function for the initial temperature before ignition, and I'll calculate a line est function for the final temperature. Okay, and so again, we're going to type equals here, and then line est, and then open parentheses, and then enter the data that it wants. So first it wants the known y values, which is these first 5 y data points, and then enter the known x values. And then I want both of these parameters, option parameters, to be true, close parentheses, return, and now I get these line est parameters. And just as a reminder, this first row of the data gives you the slope and the intercept. The second row of data gives you the standard deviation in the slope and the intercept. And then down here, this is the sigma r parameter. This is the standard deviation of the residuals parameter. Okay, I'm going to do the same thing for the final temperature. So I'm going to do a line est of these last 4 data points. So I'm going to select these ones here. Those are the known y's. Here's the known x's. And then 1, 1, and enter. Okay, and now we can calculate the difference between these two extrapolated lines at 400 seconds by just calculating the value of the final line at 400 seconds minus the initial, right? And these are, again, just the slope and intercept of a line, right? So I can calculate the final temperature at 400 seconds, right? So the value of this dotted curve right here by just calculating a function equals the slope times the x value, which is 400 seconds, so times 400 plus the y-intercept, right? So this should be something like, 24.5, right? So we got a value that's reasonable. But then I'm going to take this value that I've calculated and I'm going to subtract. So maybe I'll put this in parentheses just for clarity. So here's the final temperature evaluated at 400. And then this orange dotted curve, we want to evaluate that at 400. So I'm going to subtract that temperature evaluated at 400. So the slope times the x value, which is 400 seconds, plus the intercept. Okay, and then if I hit enter, now it tells me that the difference between the orange line curve and this whatever that is, green line curve, is about 2.26 degrees Celsius. Does that make sense? If you look at the y scale of this plot, yeah, it should be something like 24.5 minus 22.2 or something. So it looks about right. Okay. And so now what we want to do is we want to know, okay, what is 0.63 times delta t, right? So I'm going to calculate 0.63 times this delta T value. And that's about 1.42. That number looks about right to me. And so now we want to know the basically the initial temperature plus 0.63 times delta T. And as a good estimate, I can just evaluate the initial temperature at our best guess time, which was 400 seconds. So I'm going to evaluate this orange curve at 400 seconds. Okay, and so that's just going to be m times 400 seconds plus the intercept. And then I'm going to add 0.63 times delta T, which is the value of this cell here, right? So we're going to add 1.42 to that and then hit enter. And that tells me I want to evaluate the temperature rise at the time where this curve passes through a temperature of 23.62 degrees Celsius. Okay. And so again, you could do this by printing off the graph and doing it with a ruler if you want. Another way that you could do it is just by sort of drawing lines and doing it visually just within Excel. So if you go to the insert menu, you can insert a line by just going to insert shape. And then if I put a line there, then I can draw like a horizontal line over from the y-axis located at 23.6 degrees. And so if you kind of look closely here, each of these tick marks on the y-axis represents 0.1 degree. So I want to make a horizontal line and I want to put it somewhere here. So just a little bit above 23.6, right? Maybe one nudge above 23.6. That's close enough. And then I'll stretch it so that it has so I want it to have a height of 0, so it's exactly horizontal, right? And then I'll just see where's the point at which it crosses this curve. And now I just want to extrapolate a vertical line down. So I'll take this line and copy it and make a vertical line so that I can figure out, okay, what time value does this correspond to, right? This point on the curve. Okay, and so it looks like, if I try to do this as accurately as possible, it looks like it's just a little bit above this grid marking right here. And so it looks like on this x-axis scale, each of these tick marks represents 20 seconds. So it's just a little bit above 380 seconds. So maybe this is, I don't know, a little bit less than a tenth of the way between 380 and 400. So about 382, maybe a little bit less, maybe 381.5, right? You always want to, when you're reading things off of a scale, you always want to try to do it a little bit more accurately than the scale, right? So try to estimate, what percentage of the way is this reading between this tick mark and this tick mark, and add that to the tick mark. So okay, so the next thing that we want to do is we want to calculate delta T at the real time, right, where this curve passes through, 0.63, rises to 0.63 of its final value. And we said that was approximately 381.5 maybe seconds. Okay. And once we calculate the delta T, we're going to use that to, do the further calculations that you need to do to figure out the heat of formation of the compound that you're studying. Okay, but you're not going to just want to report the heat of formation. You're also going to want to know what's the uncertainty in the heat of formation. And the uncertainty in the heat of formation comes from the uncertainty in your temperature rise measurement. So we're going to want to know not just delta T, but what's the uncertainty in our determination of delta T. Okay, and so I'll make a little table. So we want to know what's Ti and what's Tf, and then we want to know what's delta T, right? And so Ti is going to equal, we just calculate it from the slope and intercept. So m times the initial, or times this time, 381.5 seconds, plus the intercept, right? And the final time is equal to m times, again, 381.5 plus the intercept, right? So here's T initial and T final, and then delta T is going to be the final minus the initial. Okay, so according to this, the temperature rise is going to be 2.26 degrees Celsius approximately. That looks about right to me. So it looks like, we probably did this correctly. Okay, but how are we going to calculate the uncertainty? There are several approaches that you could take. But the question that we're asking basically is, we've measured points along this linear portion of this line, right? If we were to measure another point somewhere along the same line, what would be the, how far would that be away from the line? And so a good way to estimate what's the uncertainty of, a value predicted along a line that you fit is to use the standard deviation of the regression for that line. So this value here, sigma r, which is, this value for the initial temperature and this value right here for the final temperature, that's a good estimate of the uncertainty in a temperature that's predicted by that fit model at another point in time. So we're just going to assume, so I'll just write this here. So assume standard deviation is given by sigma sub r. Okay, and so for the initial temperature, the standard deviation of the measurement is going to be this guy here. For the final temperature, it's going to be this one right here. Okay, and so here's the value. Here's the standard deviation. When we report an uncertainty, we don't report the standard deviation. We report the 95% confidence interval. And so we need to figure out what are the 95% confidence intervals for these two standard deviations, right? And so let me quickly bring up where's the, somewhere I have oh, here we go. So here's the lab manual. We've been using the student T table from the Excel spreadsheet, but there's also one in the lab manual. So it's right at the end of the first chapter. So if I go to the beginning of the second chapter, I can go backwards a little bit. Oh, maybe it's a bit further back. Okay, here's some tables. Here's the student T table. So Appendix B of your lab manual, this is another place where you can look up these student T parameters. Okay, so for the initial temperature, the line that we fit had n equals 5 data points, and we're fitting a line. So, to calculate a line, there's two parameters. So the number of degrees of freedom is 5 minus 2, which is 3. So we want the student T factor for 3 degrees of freedom, which is 3.18. So for the initial temperature, I'm going to calculate the 95% confidence interval as the student T factor, 3.18, times the standard deviation divided by the square root of the number of measurements that went into measuring this linear extrapolation. So that's 5. Okay, and then for the final temperature, we only included 4 data points. So the number of degrees of freedom is 4 minus 2, which is 2. And so the student T value is going to be 4.3. Okay, so here we can get the 95% confidence interval in the final temperature, and it's equal to, let's see, what did I say, 4.3? Yeah, 4.3 times the standard deviation divided by the square root of the number of measurements, which in this case was 4. Okay, and now we've calculated a value that we need, right? Delta T. This is the difference between two measured values, both of which have uncertainties associated with them. So how do we propagate the uncertainty? We add the absolute uncertainties in quadrature, right? That's what you do whenever you take a sum or a difference. Okay, and so here's the difference, delta T, but the uncertainty in delta T is going to come from adding the 95% confidence intervals on these two values in quadrature. So the uncertainty is going to be the square root of the first uncertainty squared plus the second uncertainty squared. Okay, and so we're going to see that our delta T that we've measured is 2.26 degrees Celsius plus or minus 0.04 degrees Celsius. Okay, and we're probably going to need in the next set of equations that we use to derive delta H, right? The heat of reaction, we're going to need to do further propagation of this error that we just determined. Okay, so that's just a brief tutorial on how to analyze thermograms, including how to get the uncertainty and the temperature rise. Any questions about that? Okay. Let's see. Okay. So I will close this guy. I'm going to stop the recording here. I don't think we need to record the rest.